I'm very happy to give this seminar. Yeah, so this is the topic that I'm going to talk about, and I'm going to kind of slowly explain what I mean by this. Again. Okay, so I mean, I guess everybody knows what we're talking about when we say turbulence and why it's difficult, because it's strongly interacting or highly nonlinear. It's out of equilibrium, meaning that the scale where you inject energy is not the same scale where energy gets dissipated. And then there is another complication, which is that we usually talk about incompressible fluids. And that means that things are highly non-local, right? Because if we have a perturbation, it's immediately, right, we are thinking about the sound waves as acting immediately to equilibrate the flow. So this means that it's non-local. Or a different way for people from fluid dynamics to say this is that you have the pressure, which you have to solve for, and that's a Poisson equation, which is an integral equation. So in this talk, I'm going to talk about things that are local, and that turns out to be quite helpful, and also gives sort of weird things sometimes. Okay, so again, there is this picture of turbulence of you excite energy at large scales, and then because your Reynolds number is high, dissipation is negligible at low scales, and energy goes to smaller scales until it can get dissipated. But if you were here 2 weeks ago, then you know that sort of one of the focuses of what I do, and like people that, you know, what you could call as anti-diffusive, is the opposite of this behavior, which is a self-organization of the flow as time proceeds. So if you inject energy at small scales, you can see that it could sometimes form a large mean flow. And I should emphasize that here, even though it looks very laminar, it's actually not so, and there are chaotic fluctuations, which should be important. This is a figure from an experiment from Michael Schatz's group in Australia. And the experiment is in a thin fluid layer. So this is, they put an array of magnets, and they have a thin electrolyte, and they drive a current. And this is basically the way they force the system, right? You generate these vortices of opposite signs, and this is the forcing. And if you increase the amplitude of the forcing, then this flow becomes chaotic. And if the dissipation is small enough, then what you see is that energy goes to large scales and condenses at the large scale. Okay. And one of the reasons why people find this interesting, apart from the fact that it's counterintuitive and kind of cool, is that it's believed to be relevant to large scale and persistent flows that people see in the atmosphere and in the oceans. And here there are several examples. So one is from the atmosphere of Earth, where you have the jet stream that's believed to be powered by small scale Rossby waves or eddies. There are the jets on Jupiter, which are extremely stable. So these two curves, there's a red one and there's a black one. And the time difference between these two curves is about 20 years, which is pretty impressive in how stable this is. And then, you know, a more recent photo from the poles of Jupiter, where these arrays of vortices were discovered. So of course, I'm not going to say anything about these particular flows, but that's kind of a motivation. And you could ask yourself, you know, in what sense this is a system which has, so why would you expect it to have this sort of a inverse transfer of energy or self-organization? So just to kind of put everyone on the same footing, I want to kind of generally say when you expect the situation to happen. And that's basically when you have flows with two inviscid invariants that are both positive definite and are related to each other by a derivative. The reason why inviscid invariants are important is because, as we said before, at most scales, dissipation shouldn't matter. Okay, so how does that come about? So let me give you an example of a flow. So already kind of mentioned it. This is 2D Navier-Stokes. So you have two conserved quantities. One is kinetic energy. Actually, you have more. You have any power of the vorticity, which is the curl of the velocity, that's conserved. But in particular, a positive definite square bilinear conserved quantity is what's called entropy, which is the vorticity squared. Okay, so these are the two conserved quantities that would be important. And then, right, you have this general picture where you inject energy and you inject entropy at some scale. And then what you expect from kind of the general picture of turbulence is that, well, it cannot really dissipate at these intermediate scales. So it just gets transferred to smaller and smaller scales by this constant flux until it reaches a scale where it can dissipate. But then the question is, when you have these two conserved quantities, right, in these scales, they will be conserved. Can you transfer both of them at the same time to the smaller scales? And I want to present a hand-waving argument to say that they cannot. Okay, so I introduced a cutoff, a UV cutoff, right? We're asking if both of them can go to small scales. And usually what stops the transfer to smaller and smaller scales is that you have dissipation. So it's some sort of a UV cutoff. Okay, so it's related to a dissipation. This is why I call it K nu. Okay, so let's assume that, so what I would like to argue is that the fact that both of these quantities are conserved would imply that there is a constraint and that the energy cannot actually go to small scales. It has to go to large scales, or at least it cannot go to small scales. So the argument goes as follows. So assume that you do have a finite energy at the cutoff scale, and now I'm working in Fourier space. This means that this Vk squared, which is, okay, so if I write the entropy, this is K nu squared times Vk nu squared at that scale. And if I'm assuming that the energy that reaches the cutoff scale is finite, this means that this quantity, the entropy, can become unbounded. And if that quantity is conserved, that cannot be, right? It cannot become unbounded in finite time. So this means that energy, well, it doesn't mean that it has to go to large scales, but you can imagine that you have nonlinear interactions that will eventually take it also to large scale. So it will reach large scale. So this is kind of the general argument of when do you expect this sort of self-organization. Okay, and then, okay, this only tells you that energy should go to large scales, but it doesn't tell you anything about, you know, generation of a coherent large-scale flow. So this kind of requires an additional step. So let's consider steady state. And for the entropy, so we're injecting somewhere in between in wave numbers, and the entropy just, you know, goes by a constant flux to small scales, and it can be dissipated. Even if the viscosity is small, your K nu can become very, very large. You generate very large gradients, and you can dissipate. This can, you know, dissipation can balance the injection rate. So you can have a steady state. Okay, but what happens in the other direction? So energy cannot go to small scales, so it goes to larger scales. And then the question is, how do you balance at large scales? Your K is, you know, whatever it is. It's an IR cutoff, basically, determined by the scale of your box. And you have a small viscosity. So the question is, how can you reach steady state? And the answer is that you build up a large-scale condensate. So it can be a little bit more subtle here. I'm assuming that your dissipation is by viscosity. You could have a dissipation which is by linear friction. And by changing the linear friction, you could actually stop, arrest the cascade before it condenses to this sort of coherent large-scale structure. But if you have a viscosity, you actually cannot do that. And it's always the only way to balance it is by having a lot of energy in this IR mode. Okay, and this is one of the reasons why people call this a condensate, to remind you of like Bose-Einstein condensate, where you have a lot of energy going to some K = 0 mode. Okay. And by the way, please feel free to ask questions if you have them. Okay, so I talked about the fact that you can have this in 2D flows. And these flows are in some sense quasi 2D, but there is kind of a more general class of flows where you could have these two, you can have two invariants and have this inverse cascade and transfer of energy. And the two sort of properties that I want to focus on are thin fluid layers and rotation, which are, of course, present in the atmosphere and in the ocean and on Jupiter. Okay, so for that, I'm going to consider a very kind of idealized model for the atmosphere, which goes a bit beyond just 2D Navier-Stokes, or for like atmospheric and geophysical flows. So this is a shallow layer plus rotation. Okay, so what I'm assuming is that the layer is shallow. So that means that I don't really have velocity in the z direction, and I don't really have gradients in the z direction, or rather they are small. And in that approximation, I just get one equation, which is just mass conservation, where the role of mass is played by the height of the layer. And then I have, you know, momentum conservation, and I'm in a rotating frame, so I have Coriolis force, and I'm assuming hydrostatic pressure. So this is just assuming that in the z direction, I have hydrostatic balance. Okay. And this system has a conserved quantity, which is analogous to vorticity in 2D. It's a generalization of that. And this is true for any 2D flow which can be compressible. So one important thing that I should mention, even though I'm assuming the velocity field is 2D, it can be in principle compressible because I can have, right, the surface is compressible. So dz of the vertical velocity is not necessarily small. It can be. So this comes into the fact that I have a density. So in that situation, I have, even without rotation, there is a conserved quantity, which is called potential vorticity, and that's the vorticity divided by the density. Here is the height. Okay, so it satisfies this in viscid dynamics, without forcing and dissipation. It's just advected like a passive scalar. It's not passive because it's related to the velocity. And with rotation, you have this additional rotation because the additional vorticity due to the rotation of the system. Okay, so this is a conserved quantity. And then if I take one more limit, which is to assume that I have a very fast rotation, which is called quasi-geostrophic limit. This means that the main balance in this equation is coming from Coriolis balancing the hydrostatic the pressure. And this is what you typically see, right? These contour lines are basically a reflection of that in a synoptic map, right? So then that gives you a relation between the velocity and the pressure, which is related to the height field, and through what's called a stream function, which just describes these, right, that the flow flows along the streamlines. Okay. So now that before we had two dynamical equations, one for the height and one for the velocity field, but now we have a constraint, so we can just use one equation, and that equation can be the fact that this potential vorticity is conserved. Okay, so we can just use that equation. And we'll take an additional approximation, assuming that the mean height of the layer is much larger than the perturbations. Okay, so we'll expand this just because otherwise this quantity is kind of scary because it's nonlinear in this h. So we'll do this approximation, assuming that h is much smaller than this big H. And in that case, we get this relation between this Q, which is advected, and the stream function. And this relation is interesting because here you have this is vorticity is related to the stream function just by a Laplacian. But here you have an additional length scale that comes out, which is called the Rossby deformation radius. And it's basically the frequency of gravity waves divided by the rotation rate, or the Coriolis parameter. And in a sense, what it's telling you is that it determines the range of influence of a surface deformation. So if you produce a surface deformation, you can see from this relation, if you invert it, that the influence will decay exponentially, and R would be the length scale in that exponent. Okay.
Sorry, slide when you say at the bottom,
yes,
when you always absolutely give those scales, but that's really small layers.
Okay. Okay. So yeah, thank you for the correction. And okay, you're saying, but because you're saying that here what would appear is not this square root of GH, but the buoyancy frequency. Okay, so you need to use something. It's not this R, but related R. Okay, so thank you for thank you for the correction. I will disappear this in the next round. Okay. Okay, so yeah, so what I'm interested in is kind of asking about the limits of this equation. So if I take the limit of this Rossby deformation radius to infinity, then I basically get 2D Navier-Stokes, right? This is sort of the limit of incompressible 2D Navier-Stokes. The waves, the gravity waves can equilibrate the surface and it just stays flat. But the other limit, which is kind of more strange, is when you're taking this R to 0. It's a bit of a tricky limit because in the leading order, it just gives you no dynamics. But you can take the next order and it is consistent with other approximations that I've taken. You can show that. And then what you get is sort of a mirror image of the R going to infinity. So here, what's advected, what is the kind of passive or active scalar is the vorticity, and the advection velocity is related to the stream function. Whereas here, what's advected is the stream function or the height, and the velocity of advection is related to the vorticity, which serves like a stream function, which is confusing, but okay, that's what you Okay. And now we're going to ask about the self-organization of this flow. And we're going to add small-scale forcing and dissipation and ask about the steady states that the system gets, and in particular, these large-scale structures and what they would look like in this state. So one question you could ask is what actually determines the structure of the large-scale flow? Okay, so maybe I didn't say this explicitly, but since that system has a conserved quantity, which is the energy, but also Q squared, which is potential vorticity squared, you do expect here this self-organization to emerge. And one question you could ask is, okay, what would determine the structure of this large-scale flow? And an obvious question would be, okay, it will take the largest scale because it's only when it reaches the largest scale that it can condense there and lead to a steady state. And the other thing is that, okay, it will conform with the domain symmetries. This is what you would expect in general, because there is no other, there's no other rule to say otherwise. And this is correct in 2D Navier-Stokes. This is what you see. So if you force at small scales, right, because you want to see what emerges at large scales and hope that it's universal if the small scale forcing is small enough. So if you force, this is in simulations, if you force with homogeneous and isotropic wide in time forcing, so you're not putting in any funny things at small scales and you just see what emerges at large scales and you take a doubly periodic domain because this is what you do usually in simulations, then what you get, if you are in a square domain of the aspect ratio 1, then you get a dipole. And then if you change the aspect ratio a little bit, then you can get jets just because you break the symmetry externally. Okay, and this is well known. This has been studied by Freddie Boucher and Simonet, I think, initially. And then I think 2 weeks back, we heard a talk by Andrew Van Pan where he kind of studied transitions between the two states in this aspect ratio a little bit larger than 1. But you are breaking the symmetry externally. And so this is what you do expect, right? You've broken the symmetry. So you will get jets. The reason why I'm saying these are jets is because there are open streamlines here and there are no open streamlines here. So the symmetry is broken. Okay. Yeah, sorry, I'm just, this is the color code is just the velocity. So in the green regions, you have a hyperbolic point. So this is like a stagnation point. And these are 2 vortices. So you need to get 2 vortices, a dipole and not a single one in this system because we are forcing. So because the box is periodic and we are forcing with zero mean vorticity. So you have to have the 2 signs. Okay. So then a question you could ask is, well, if I change the range of interactions, what role does that play? What is universal? What is not? And so we're going to consider the condensate in LQG. And so before I tell you basically what is not universal, let me tell you in one slide what is universal. Okay. So, sorry, before that. Okay, I'll just introduce the invariance of the LQG system. So it basically decomposes into 2 parts, both of which are energy. So you have the available potential energy. So recall that psi squared, psi is like the height. Okay, so this is the potential energy. And then you have the kinetic energy. So recall that grad psi is related to the velocity. Okay, these are the 2 invariants. And now you know which one would go to large scales and which one would go to small scales, right? So the one with a derivative would go to the small scales. The one without a derivative would go to large scales, okay? And so you expect condensation of this psi field, okay? Okay, and this is what we studied in a work that we published. And this is what I wanted to tell you about what is universal in one slide. Sorry. Okay, so one thing you could do is in this system is you can do a very nice theory because the system is local, so you don't have the annoying pressure to deal with. And that's why perturbation theory works very well. So here perturbation theory works well because you have that condensate, which is very strong, and you have weak fluctuations. Although the fluctuations are weak, they are important because without them, the condensate would not be sustained. It's the transfer of energy from the fluctuations to the mean flow. And then a lesson that we've learned by doing this sort of calculation in this LQG and in 2D Navier-Stokes is that the second order correlation functions have this general form. So there are 2 parts to it. Okay, if you have a mean flow, this means that you've broken parity, okay, because you have the direction of the mean flow. So just assume locally it's some kind of shear or something like that. So you have a direction that you've chosen. And another thing is that you can consider time reversal breaking, okay, symmetry breaking. Now, just having a mean flow doesn't break clarity plus time reversal, okay? Because you flip the space and you flip time and you get the same thing. And this is a symmetry of the Euler equation. But, okay, so in this system where it is very strongly out of equilibrium, you can do this sort of closure and compute the mean flow and then look at the 2-point correlation function. And what you find is that the equation for the 2-point correlation function decomposes into two parts. There is a part which is related to advection by the mean flow, okay, and related to the homogeneous solution to this equation. And that part is even under this PT symmetry. These are zero modes of this advection operator, okay? And the other part, which is odd under this PT symmetry, is a solution to the inhomogeneous equation. And the inhomogeneous equation, the forcing is the thing that breaks PT symmetry because it breaks explicitly the time reversal symmetry, okay? And I think that this sort of picture could perhaps apply also to 3D flows, but the thing when you have a strong mean flow, but the difference is then the thing that should break time reversal symmetry is actually the dissipation and not the forcing. So in 2D, you don't have a dissipative anomaly for the energy, and this is why you don't have that. Okay, so sorry, this was, I don't know if this was understandable, but sorry? Yeah, so I mean, I kind of didn't say anything, but the prime, you have a psi, the average psi, and you have the fluctuations around the average, and the prime is just the fluctuations. So this is a correlation function for the fluctuations field. Okay, I mean, yeah, I'm not saying, I understand that this is not understandable, but that's not the main point of the talk. I just wanted to flash this. No, you can have gradients. It can be general. Yes, it's true. So what we were looking at in that case was actually a rectangular domain. And then you had, I think that statement should still sort of be locally true. But the case that we were considering is really where you have a jet. So there is one direction in which it's pointing, and there is another direction where it's changing. And in that case, you really have, you have reflection symmetry in that direction. Yeah, exactly. So you can really do that. But I kind of suspect that something local like that could still work, even when you have something more complicated. Yeah. Okay. But what I wanted to tell you about is something that's different from 2D Navier-Stokes. Sorry. So I spoiled the thing. So if you do a simulation in a square box, I told you that what you expect is this kind of dipole structure. But if you wait long enough for the steady state, you sometimes get jets and not a dipole structure. And here the symmetry has not been broken not by the boundaries, not by the forcing. Okay, and I would like to explain why this happens. Okay, so first let me kind of tell you the zoology of the things that we find. So we don't just find jets or just dipoles, we find all kinds of solutions with different broken symmetries. So one kind of solution we find is this dipole, where you have the two vortices. Another kind is where you have two symmetric jets. So here you have a pi/2 rotational symmetry. Here you have a pi rotational symmetry. And here you just have broken all the symmetries. So you have one straight jet and one bent jet. Okay? And the transition between these two, okay, so you have actually several parameters in this, several dimensionless numbers in the system. But the ones that we found to be important are two. One is Kf over Knu. So if you recall, Kf is the forcing scale, Knu is the UV cutoff, and Kf over Knu tells you how wide is the direct cascade, right? The cascade of the kinetic energy in this case. And the other one is Kf times L. So this is forcing scale versus IR cutoff. How large is this inverse transfer range, which is related to the potential energy? This one actually plays a lesser role than this one. Okay, so here we're of course changing both of those because we're changing the distance of Kf from both things. But I will try to convince you that this is the important part mostly. Okay, so as you increase Kf, you see that you transition from dipoles to jets. Okay, all these states have been started from zero initial condition. You have stochastic forcing at small scales, and you reach a steady state after a very long time. And you get either that or that or that, depending on the Kf. But you could also ask, let me start from this state and change the Kf adiabatically and see what kind of steady state do I get. And this is what my student, which I should say, Anton Svirsky, did This is his work. Okay. So he started from a dipole and then increased Kf and waited. So he tried to do this slow enough so that each time he reached a steady state. So you see that you start from a dipole and then you stay in a dipole, even though you can see that here it's very squished, here it's kind of less squished, and then all of a sudden you transition to just jets. Okay? Then you can also start from the jets. Okay, so you start from the jet, you become symmetric, and then maybe you switch to a dipole. It's not quite clear. Okay, it's not clear if it's probably a dipole, but maybe it could be also the symmetric jet. Okay. Sorry. Yes.
Are these instantaneous snapshots or are these
these are averaged over a short time.
Values of K. This is relative to what we
Yes.
this is the box.
Yes. So this was written hidden in this slide that it's always in units of L. So KFL. I mean, actually, when I'm writing KF, this is KFL. Okay, sorry. And my KNU was fixed there. Okay. Sorry. Okay, so what is the picture that we get? It's this one. So I'm starting from a dipole here, and I can stay on the dipole branch up until here. But after I cross this point, I transition to these jets. If I start from the jets, then I smoothly go to symmetric jets. And he also started one of the simulations in the symmetric jets and went either here or there, and it seemed to basically reproduce the same curve. When you are over here, you have stochastic transitions between the two states. Okay, so this is why, like here, he has a point here and a point here. Okay. When he's here, he is never observed transitions. Okay, so the picture is sort of like a bifurcation diagram. Of course, you should take it with a grain of salt because these are, you could think about the bifurcations of the large-scale flow, but you always have fluctuations. So at this point, right, you can't really distinguish between unstable. There's no need. Okay, so that's the picture, is that you have the dipole state. It loses, you lose it. Either it cannot exist or it's unstable. And at some point, you do have a bifurcation, or you have these two branches that break the symmetry. These are the jets that could be either in the x direction or in the y direction. And then there are two additional branching points, which are these ones where one of the jets would be straight and the other would be not straight. Okay, so why do you see this zoo of states when you change KF? So for that, I need to tell you an additional piece of information that we found in our previous study of this system. Okay, so first of all, to read these plots, you can really think about these orange areas. It's basically showing you the area of the condensate, because this is actually where most of the dissipation of the potential energy is occurring, okay? So this is where large-scale dissipation of potential energy is important. So this is basically the area of the condensate. And when we did, so this is from different simulations where the box had explicitly broken symmetry and you had these very uniform jets. And what we found is that if you look at the dissipation of kinetic energy, so I remind you that kinetic energy is the thing that goes to small scales, it's always concentrated away from where the jets are, right? So I'm telling you that this is where the condensate, this very strong amplitude flow is. And here it's very weak. But when you look at the kinetic energy dissipation, it's all concentrated in these very weak regions. And since we could solve that system analytically, perturbatively, we could also compute, we could look at the kinetic energy balance. So usually in 2D Navier-Stokes, that kinetic energy balance is not very interesting. It's usually just you have kinetic energy injection, or it's the entropy there. It's entropy injection and then dissipation, and you just have a balance between these two because energy goes to small scales. But what's happening here is that you have a spatial flux term, and that spatial flux is taking the energy, the kinetic energy from these regions, and it's moving it to other regions. So basically, you have an arrest of the direct cascade in space. So we're used to thinking about these inverse and direct cascades in Fourier space, but here there is actual space that plays a role. Okay. And another important point for this is that the type of, I didn't really say this explicitly, but what we use for the dissipation of the potential energy or the height field is potential energy is a kind of viscous term, which is actually linear friction on the velocity, and that term conserves mass flux. Okay, and in 2D Navier-Stokes, this is kind of the difference between using linear friction, which doesn't conserve momentum, and using viscosity, which does conserve momentum. And it turns out that in the case that you're using something that does conserve the momentum, or here mass flux, then you do not have any flux of potential energy for symmetry reasons into the condensate. So whatever energy you're injecting in this area locally gets dissipated in this area locally at large scales, and there is no flux from outside regions. And this is different from what people observed in 2D Navier-Stokes. But even though this is the case, I want to emphasize that in 2D Navier-Stokes, the small scale dissipation is pretty much uniform. It's not exactly uniform, but it's really not this binary. Okay, it changes by, I don't know, maybe 20%. Okay. So these, who is keeping time? Someone keeping time, or? I'm doing fine. How much time do I have? 20 minutes. Okay. I'm just wondering if I should go into an explanation of how do you get. Okay. So what I want to, like, my next point would be that when I'm changing KF, what I'm doing is I'm changing the area of the condensate, because there is a constraint from energy balances in space, which kind of tells me what should be the area outside the condensate. So let me try to explain it. Okay, so what we're doing when we're injecting, so let's talk about kinetic energy first. We're injecting it uniformly. That's just the way our forcing works. We're injecting it homogeneously in the entire box. Okay, and there is basically no large scale dissipation of that quantity. Okay, it's all basically going to small scales. And what I told you is that this is only the small scale dissipation of the kinetic energy is only occurring in the intercondensate area, not inside the condensate. Okay, so this means that the total entropy that I'm injecting has to be all of it dissipated in this region. So this means that the flux and the dissipation in this region has to increase by a factor that's related to the size of the domain. Okay, so that is telling me what is the energy dissipation rate in this region, which is also the kinetic energy flux, okay, in those regions. Okay, now I can do the balance of the potential energy. So again, I'm injecting it homogeneously. I told you that it gets dissipated only locally, but there is always a small fraction of energy that is dissipated, of potential energy, that gets carried by the kinetic energy in this case to the small scales and will be dissipated there. And this is what I call epsilon nu. Okay, so the total energy injection, potential energy injection, should equal what I'm dissipating at the large scales plus what I'm dissipating at the small scales. And this means in particular that in this entire area, I have to dissipate exactly what I've injected here, because I don't have any other source of dissipation, okay? Because there is no condensate there. Okay, and then you can also recall that the connection between the kinetic energy and the potential energy is by this k nu squared. Okay, so you can relate the two. And this is also true at the injection, because I'm injecting at a particular scale. And these things put together give me the constraint that this area has to be exactly so that I get the energy that's getting the potential energy that gets dissipated at small scales is exactly equal to this epsilon nu. And this gives me this constraint on the area of the condensate that has to be 1 minus kf over k nu squared. Okay, so put in another words, or to summarize, the residual small scale potential energy dissipation is concentrated in the intercondensate area, and that fixes the area to be such that it compensates the local energy injection, right? So I always have some small scale dissipation of my potential energy, that because my direct cascade is finite, whenever I have a finite UV cutoff, and that part of the energy that dissipates at small scales cannot be dissipated inside the condensate, it can only be dissipated outside of it. And outside of it, it is the only source of potential energy dissipation. So that sets the size of that area, okay? And in particular, if I take this direct cascade range to be infinite, right? So I'm taking Kf, I'm taking K nu basically to infinity compared to Kf, then I see that my condensate then should fill the entire box. And this is indeed the trend that you're seeing here, where this is for a smaller Kf, you see that with fixed K nu, you see that the regions that are black are much smaller. Okay? Yes.
I'm not sure how you is supposed to be.
No, so you just do sort of dimensional analysis. You have the viscosity. So here it's actually hyperviscosity. And you have the energy injection rate. And from these two, you can just, right, the condition is that your dissipation should equal your injection rate.
So
it's just a Kolmogorov scale. Yeah, exactly. So this is why, yeah, okay, this is why we're using the white in time forcing, because then you don't really need to, right? You know, for white in time forcing, you can determine the amplitude, like the injection rate. It's determined by the amplitude of forcing. So if you're doing it smartly, you can keep the energy injection rate fixed and only adjust Kf. I think that at the time we didn't really think about it so carefully, so we kind of changed both. But I don't think that, I mean, everything is kind of normalized so that you don't actually see it. Yes? Yes, true. You'll see that in the, yeah. I think the strength of the forcing, again, I don't think it plays a role, but I should think about this more carefully. I mean, I think there are additional dimensionless parameters, like what I mean, you could think about the ratio between your injection rate and the dissipation rate at large scales, for example. So that's like the parameter that you're talking about. But I think that would only tell you indeed about something about the amplitude of the condensate. But in this balance sort of equation, it doesn't really change anything, right? Not really, not by shearing. Well, in a sense, yes, but again, it's by kind of my previous argument, the main thing is the amplitude of the condensate, right? The amplitude grows to be very large because the shear is not very effective. It's at the box scale. Okay, so to convince you that this is what's going on, what you can do is you can define the area of the condensate. So this is, okay, you can motivate why it should be a fraction of square root of epsilon over alpha from theoretical considerations. And what you see is indeed, like these are all the simulations that Anton did with different K nus and different Kfs. And you see that they sort of follow this trend. Okay, and if we believe this, then we can try and explain why do we get a transition between the dipole to the jet. Okay, so if we start, so what this relation is telling us is if we look at the area of the condensate as a function of Kf over K nu squared, as they increase, the area of the condensate should decrease. And at some point, I'll reach the point where these two vortices are exactly touching. And if I increase it more, then they should not be touching anymore. And that sort of contradicts the mantra that we have, which is that the flow should form on the largest available scale in the box. And a way to understand it is that if it doesn't, then, well, there will be a flux to larger scales that will build something that is on a larger scale. Okay, and just by geometrical considerations, you can say at what value this should occur. And this gives you a Kf over K nu squared that is approximately 0.21. Okay, and then you could also ask a bit about the phenomenology of what you're seeing. So what happens when we increase Kf over K nu, and what is happening with this branch, with this solution. So let me start from this point where the two jets are basically straight, but you can't really distinguish between one of them being straight and one being bent, or the other one being straight and being bent, because it's sort of you go between the two by fluctuation. And this configuration is special because here the vortex is of its minimal size, it appears to be, of the forcing scale. So not to say that we understand why a vortex of the forcing scale is the minimal thing you can have, but this is what we observe empirically. And then what's a bit funny is that if you increase kf over k nu, what happens is you have to increase the area. And the way that you do it is by increasing the size of the vortex. And then you have more gaps here, right? So this is this phase. But then if you decrease kf over k nu, again, you do the same thing. You increase the size of the vortex, but now you have these two jets which are hugging it. Okay, so that's the way you satisfy this constraint. Okay, so this is kind of the terminology of what we're observing. Okay, and to kind of end with something that's kind of nice, I think. So what I told you is that if kf over k nu is larger than 0.4, which is, quite large, but okay, and you imagine, so you have sort of, you have a finite UV cutoff, but you take your IR cutoff to infinity, right? So this would be a sort of thermodynamic limit, right? I'm taking the box to be infinite, okay? Yes, I can, yes, or I could do another thing. I could take kf and k nu, fix their ratio, and send both to be very large, right? So that's the same thing as, right? So, but I do want to keep this ratio larger than this, but fixed, and then send kf times L to infinity, right? And in this limit, what we are observing and what we expect is, we are not observing this limit, but what we expect to get is, from that consideration that I showed you before, is one of these four configurations, right? You have one straight jet, one bent jet, and they can be in either direction, and it could be either of these jets. And the question is this a spontaneous symmetry breaking, in the sense that when I take this thermodynamic limit, will I get stuck in one of these states? Or maybe I can fluctuate between the different states, because we do see fluctuations between like dipoles and jets. And what I want to argue is that in this limit, we do not expect to see transitions between them, because in order to transition between them, you will have to close this gap. So you need a system size fluctuation, which I expect to become, improbable with the scale with the system size, okay? So I do expect that in the thermodynamic limit, there will be a spontaneous symmetry breaking, right? And it's spontaneous because it's really forced by the sort of spatial fluxes of energy, and there is nothing external that breaks the symmetry. Okay, so just to summarize, so if you have two positive invariants that are related by a derivative, then the flow can self-organize. The range of fluid interactions can influence the spatial distribution of equilibrium fluxes. And we think this is, so maybe similar things you'll be able to see in other systems where you have a finite deformation radius, which is smaller than the forcing scale. And in this kind of funny system where this Rossby deformation radius goes to 0, then the self-organization is really affected by this partitioning between the out of equilibrium fluxes in space. And you can have a spontaneous symmetry breaking, which is driven by the fact that you have a finite UV cutoff and it's not sent to infinity. Okay, so, and this is so this is Anton, my student with which we did this work, and this is Colin Herbert, who's a collaborator, and this is a kind of a phase diagram. So not in what Pat suggested, but in KFL and KF over K nu. So KF versus IR cutoff, KF versus UV cutoff, and these are kind of the different simulations that he did. And these are sort of the boundaries that we expect to see between the different states. Yeah, I think the boundary that I discussed with you was this blue one, and here there are these squares which tell you that these are the jets. There are some points which are not exactly in this boundary, but okay, more or less this agrees with what we expect. So with this, I will finish, and thank you for your attention. Yes. No. Of course.
Because it was processed.
No, of course we did center it, right? I mean, there is a spontaneous translation of symmetry that's broken. But I think that in this case, like if you do these simulations in 2D Navier-Stokes, I think the vortices do drift because they influence each other. But I hope I'm not saying something wrong, but I think in this system, they actually don't drift. They probably do diffuse over a long time scale. But I don't think you really need to kind of fix all the snapshots so that they align. You don't need to post-process to align things because I think they sort of get stuck there more or less for a long time. No, they don't know anything about where the boundaries are. It's just a timescale separation thing. I think that if you look at long enough timescales, they will diffuse in the box. Yeah, they definitely do not know anything about them. There is translation invariance. Yeah, and what Basil was talking about. Yes. Yeah, this is a super out of equilibrium effect, right? Yeah, I don't know. I mean, I think that so maybe I misunderstood, but kind of my impression of that was that it's more about the amplitude and less about the structure. So, and the amplitude, I mean, and it's also about the fact that you have two effects and you have some partitioning of energy between these two effects of the same energy, right? The energy there versus entropy. But here it's all about, I mean, the amplitude, you don't really have a partitioning of the same quantity between two objects. And the amplitude would just, follow by basically energy conservation at large scale. Steady state at large scale. But yeah, I don't know if you could, right? That's the question, if you can get a structure from minimum entropy argument here. And it's really, right? It's really related to a fact that, well, I don't know. I mean, we computed this for jets, but we don't really know why it has this feature where you have this special flux outside of the condensate region that concentrates all the kinetic energy dissipation or transfer to small scales outside of the condensate. So this, we don't actually understand why that happened. But of course, it's a very out of equilibrium effect in which you couldn't capture in statistical mechanics kind of thing. And classical statistical mechanics.
So, did you look for drifting of the asymmetric space? Because generally you would expect that.
Yes. No, we haven't. I mean, maybe Anton did, but I never talked to him about it so much. I mean, we did kind of in the work where we considered this. These ones. We did try to do various centering. I mean, sorry. So this is like an aspect ratio that's not one, and then you just get jets. You break the symmetry explicitly. And then you could also ask if you have some drift. I know there is no symmetry breaking, but okay, you're saying in the states where there is. Yeah. Yeah. Yeah.
But if you break to
Interesting. Okay. No, I mean, I don't know. I don't know. But
it'll be slow. So.
Yeah, I think that Anton is not spinning things, but maybe I'm wrong. So I'm not sure. He might be for his analysis. Maybe to make it clearer that he is. The what?
You said you explicitly said you're getting rid of the global.
No, yeah. So yeah, so I didn't explain this, but it is true, I believe. So so this is here. It's because what your stream function is the derivative of the scalar that you're advecting. So like the velocity, right? The non-local nature is coming from the fact that, okay, so psi is your active scalar, and the velocity with which you're advecting is usually related to an integral over psi, or right, an integral over the, let's call the active scalar q. So usually you have dtq plus v dot grad q, and then the v is related to an integral over q. But here it's related to a derivative over q and not an integral, because omega is the vorticity And that's why things are local. And that's the thing that makes it there is no inversion, exactly. There is no inversion. Everything is just like, just local. Mm. Yeah. I don't know. The honest answer is I don't know. I think that if they were there, Anton would see them. Maybe they're there and unstable. But also, I don't quite see how, I don't know. I would have to think about it. Exactly how those would look like. Yeah. But, but interesting point.
And ask about your C delta.
Yes. That's a good point. I think it's small, but it is different between different runs. So I don't know if Anton wrote what C delta is. Of course, I stole his slides, so I think he didn't write, and I think it was not large. But the point is that it depends a little bit on the boundaries. Like what I'm saying is I'm saying there is a sharp cutoff between what I call a condensate, what I don't call a condensate, and there is a small dependence on the boundary because this is where you could have boundary layers and a lot of dissipation, and this could affect things a little bit. But this trend here he is using just one C delta, which is constant and not large. But he said that when he tried to look at it a bit more carefully, there were actually different constants for slightly different ones for different ones. Yes. But in the thermodynamic, okay, so I should say this is the preliminary one. Yes? Mm. So in the thermodynamic limit, you're going here, and this goes down here. And so if you are below this line, you would have a coexistence between the. Yes, we do expect. Yes, because this is exactly this kind of minimal vortex that I was telling you about, and that minimal vortex shrinks as you take KFL to infinity. So yeah, we do expect that to shrink to zero. Yes.
So could you get a system like this from any other physics, right? I mean, you've chosen a particular.
So I should have said because these are the same equations for plasma. I am doing something that's not typical, which is usually you also need to take into account the gradient of the rotation. And so in the case, my R in plasma is the gyration radius. So there is similar physics, but I am ignoring in that case the drift. So. Yeah, so I didn't mention it because my knowledge in plasma is embarrassing. So that's why I didn't mention it. But it's the same equation. So you could imagine that you would have similar physics if that radius is much smaller than where energy is getting injected.
Okay.
Thank you.